All right, now we come to that was also the base web search. Now let's come to link structure analysis, which is most famously associated with PageRank. And this comes back to the issue we already discussed, namely about relevance. And relevance depends on what the user really wanted. Um, and there is the type of information that Wikipedia is aimed to answer, which is like when you do Roman Empire, um, you want to have a rich set of information about Roman Empire. One thing I use search engine for is spelling. I type a word at the search engine, and when I do type a single word at the search engine, usually the search engine is pretty clever. It knows I want to spell because it gives me the dictionary what I want to spell or check the exact meaning of. Sometimes in my I forget things nowadays, and I want to check that uh, I'm using a word in the right fashion. So I want the dictionary definition of the word. So I just type that word at the search engine. That's sort of informational. Navigational. Well, if I'm flying United.com, which I am about to do later today, flying to Chicago from Indianapolis, I would want the United.com website. And that's finding home pages. This is an Israeli slide, and so for Israel, the airline is El Al. And another example here is I want to buy a camera or a battery or something like that. So you want to find results which are people that sell cameras. So depending, you have to try to look at what's typed in and ask what the user really wants. So that's, if you like, if we view the query as data, we're trying to find what the informational knowledge behind that data is. The words in that query are the data, but remember, everything is data, information, knowledge. So we need some processing to find the knowledge implied by that query. So a pretty important idea is that of anchor text. We've already mentioned anchor text before. And so when you have a web page and you hyperlink another page to it, you have that hyperlink associated with some text on your page. So that is you're making page A, but you're referring to page B. And what you say when you hyperlink when you go to page 8 can often be pretty insightful as to why page 8 is useful or maybe not so useful. And so those anchor text is often very useful in defining page B and might actually give an overview of what's in page B more precisely than actually page B itself. So that's these so-called navigational queries. They use the anchor text to try to get back good answers. We will see a couple of famous results here, one for the query French military victories and the other for engine. Let's look at that. So we mentioned a couple of examples. One was the French military victories example. If you look at the first site returned for that, it actually is an example of a Google joke where you get French military defeats instead. And that is an example, somewhat flaky example of how the anchor text can overwrite the meaning of a page. The other example, I think, is a more sounder one. And if you type engine into Bing, then one of the returned items is Google. And the Google page does not have the word engine on it, but of course this is the Google search engine. So that points out that the way these search engines work, they've already got some hidden association between search an engine, so that when you type engine, it actually goes and looks for search engines. So that's a good example of what these search engines return is a relatively sophisticated result of analyzing what you really want. So that is partly quantified in this slide here. So as well as the anchor text, just what links to what is important. So because we're trying to find that when you type X, maybe you really meant Y, where X and Y are terms or phrases. And one way you can do that is through, say, for anchor text, we're going from page A to page B. So that is in some sense, the idea of PageRank is that that's a recommendation of A's author that B is a great page. It's also an evidence that A and B share some topic of interest. We can also do it in a more complicated fashion by having a single page C. If it points to A and to B, there is some sort of link between A and B. They may actually be on different items because C could be a broad page and could cover various things, and it would point to A and B, but they're still probably related because C is probably a coherent discussion of something. So an early idea from Kleinberg was the concept of hubs and authorities, and those are still pretty important concepts. So authorities are things like Wikipedia or encyclopedia or dictionaries, which are pages containing authoritative content on a particular topic. That's often what you want, but one way of getting such authoritative information is to go to a hub, which is a list of multiple links, which each link of which is relevant to a particular topic. And so HITS was an early technology which took a topic and found you hubs and authorities. So that's an example of a data analytics, and modern search engines have such data analytics. And we won't discuss HITS, but we'll touch on related ideas later on in this unit. So here is Paramount.com, which is an authority for the query movies, because obviously Paramount is a big movie company, movie making company, I should say. Here is a hub, which is finding movies.html on the web, and I don't quite know the site ENN, but it came from this. But obviously, what you see here, you actually see Paramount Pictures, Disney, 20th Century Fox, MGM, Sony, Universal. These are all famous movie companies. So this is an example of a hub, which is a hub for movies. And so when you type movie, getting such hubs is a good idea, because then you can see quickly what you might want. Now we come on a few slides discussing this technology PageRank. Later on, there's actually some software which we will look at, but to calculate PageRank, either PageRank of a particular real page on the internet, or take a graph of websites linking to each other and calculate PageRank from that graph. And Page refers to Google's co-founder, Larry Page, whose PhD discussed this. And it is effectively a measure of the importance of a web page. And the idea is a page is important if it receives many links. And also, the importance of a link is more important if the page is important. And it is actually relatively simple. It's like many elegant, clever ideas. It's actually pretty simple. It's not difficult to calculate. And it is, as it says here, based on a random walk or a Markov chain idea. For the purpose of these lectures, Markov chains are roughly random walks. And we look at what happens when we have people or agents moving through the internet, and at any stage they're on a page, and they either select equally from all the links on the page another page and go to it. So do that 85% of the time. So any one page has gone to 0.85 over the number of links on the page times, or it goes 15% of the time. This number of 85 and 15, which might add up to 100, they can be chosen to different values. These are just typical values. And 15% of the time, it will just go to a general link. Naively, that means the person goes up to the top of his browser and types in a new link into the web page and goes there. Here's an example from Wikipedia of pages. Each happy face is a page. We have pages here which point to other pages, either to this yellow page or this blue page, and these pages here are not pointed to by anybody. You only get to them if you actually use the 0.15 probability of typing the URL into the web browser. There's a yellow thing up here, the really happy thing, has lots of people pointing at that page. So the size of the happy face is the so-called page size proportional to the size of the page rank, which is calculated iteratively by assuming the page rank of all the pages. Then you recalculate the page rank given their current importance and who links to who. You can then calculate a new value, and then you just iterate that idea, and you'll find it will actually converge. It's good when things converge. Some things actually always converge. That always converges. Here we actually write it out a bit mathematically. That the page rank of page I. This is if D is 1. We only consider links. The case when we can link to a page is page rank of page I is the sum over pages J pointing to I of the page rank of J over the number of pages linked to page J. Then you would take D times this and 1 minus D times the chance that you type in a random URL. And as we will quantify in the later lecture, we get a matrix equation. The thing becomes matrix multiplication. What you get out of that matrix multiplication done many times, that gives you the so-called PAR method of finding the eigenvector of largest eigenvalue of this particular problem, and that is the eigenvalue is the page rank, and the eigenvector is the set of the eigenvalue is 1, and the eigenvector is the has components which are the page ranks. So here's another example of a bunch of graph. The graph is defined by who points to who. So this page D has 2 links going to A and B. And then we have all these small things here which don't have anybody pointing to them, but they themselves point to things. And then we can calculate the page rank. Look at C here. It's big because B doesn't actually point to anything except C. So C is big and inherits the importance of B. B is pointed to by a lot of people. Notice it's not quite as popular as B because of the fact that D is 0.85. And so there's some probability that we don't actually go to C from B. So it's sort of interesting. This concept can be generalized because you can think of page rank as a reputation. It's either, in the web page example, it's the importance of a web page, which is similar to the reputation of a web page. And so you can use this concept with other types of entities. One of the examples is trying to rank journals. There is a so-called eigenfactor method of ranking journals, which is just effectively using the PageRank idea, which apply it to journals where the linkage now doesn't come from people from hyperlinks within the directly from actual physical hyperlinks from one article to another or one journal to another journal. It comes from citations. So the citations of the articles in the journal effectively establish a graph. When you analyze that graph, you can find the same type of eigenvalues and eigenvectors, and that then gives you, again, the most popular journals and things like that. And another similar example, which has been used, is to apply this to rank essentially universities or research programs, and you again link people together by seeing which universities place students in other universities. In the case of eigenfactor, it competes with a simpler concept, the impact factor. The impact factor of a journal is the average number of citations that every article in the journal gets. That's a much simpler concept, and that's actually what people tend to use. But maybe eigenfactors is better. So here's actually, if you go to the eigenfactor website, you can find out that actually you get sort of sensible answers, Nature and Proceedings of the National Academy of Sciences as top journals with good eigenfactor coefficients. Science article, here's a journal I used to publish in, Fisher Letters. It's a very key physics journal which has short descriptions of the latest physics discoveries. PhysRev has a good eigenfactor. It is the longer version of that. In physics, these journals sort of are dominant. So, I mean, part of this reflects the fact that in some fields have dominant journals. Other fields, actually like computer science, tend not to have dominant journals. And so they don't get such highly rated, whether by impact factor or eigenfactor, they do not get such highly rated journals.